So Yonit, we can start if you're ready.
Sure.
Okay, so good morning, everybody. Welcome to this last week of the Invisible School. This is the week of the dark matter. We have the great pleasure to have with us Yonit Talkberg today with us from the Hebrew University of Jerusalem. And she's going to speak us and teach us essentially dark matter, what is the basis of dark matter and some applications. Remember that on Friday will be on Thursday, there will be the tutoring lecture given by Michele Scudero, and again there will be Yonit on Friday. So there has been this little change in the schedule for this week. And remember the visit to the laboratory dark matter experiment for Friday in the last moment. Please, Yonit, go ahead.
Okay, thank you so much. So hi everyone, it's really nice to meet you. Although it's unfortunate that we're not meeting in person, I'm still really excited to be here with you guys today. And so as Luca said, these are going to be lectures about dark matter. Okay, typo there, in Invisibles21. So I'm really excited to be talking with you guys today and for the rest of this week. So as Luca said, the rough plan for this week, which is somewhat different from what I think you've had so far. So we're going to have 3 lectures, so 1.5 hours times 3. And then actually on Thursday we're going to have a 1-hour TA session, and then we're going to have, a 1.5-hour TA session, and then we're going to have 1 hour together on Friday. And what I hope to give you sort of a taste for in this week is, dark matter is a very, very broad and active field of research, and obviously I can't hope to cover, nor would I ever presume to cover everything that's interesting to be said in this field. But what I do want to convey to you is sort of give you a little bit of a taste of what I find to be exciting developments, and to show you a lot of the sort of tricks and tools and back of the envelope type of methods that we use in order to really try to give you a little bit of a feel for the type of stuff that's difficult to get if you're just reading through a paper or reading through a book. So that's really my goal for you at the end of this week, to get so you can have a sense of how you can sort of do these use these tricks and try to understand how you can get to interesting results, or realize if an idea that you have is interesting or less interesting. Okay, and sort of the general ballpark of sort of the outline for these lectures. So we're going to start, and this is what we're going to be doing today, with some intro to dark matter in general, and sort of a cheat sheet of early universe cosmology that we're going to need. Then we're going to delve into talking about mechanisms for setting the relic abundance. We'll talk a little bit about different models in this context, and then on Friday we're going to get to detection. Okay, so that's the general plan. And let's just lay out what the outline is really planned for today. Okay, so for our first lesson today, here's our outline. So we're going to start with a short intro. Okay, what we do and don't know about dark matter. I'm going to give you a short cheat sheet for early universe cosmology. Sort of picking out the pieces that we're going to be needing in order to make progress together. And then we're going to start talking about mechanisms. In particular, we're going to start today with talking about 2-to-2 mechanisms. One of them in particular, which is what I'm hoping we'll be reaching today, is talking about the WIMP. And then tomorrow, and as we move forward, we're going to be going into many other mechanisms, and also moving beyond just 2-to-2. But that's our plan for today. So let's start at the beginning. What we know and don't know about dark matter. Okay, so here's what we know and don't know. Okay, so we know that dark matter, and dark matter I'll often be just denoting shorthandedly as DM, that'll be dark matter over here. We know that dark matter makes up 27% of the energy content of the universe. Okay, Okay, so this roughly means if I'm thinking of comparing my dark matter density compared to ordinary matter, to baryons that we have, and we know, that means that the energy density in dark matter is roughly 5 times that's sitting in baryons. Okay? Now, how do we know this? We know this in a bunch of different ways, and I'm just going to sort of sketch through them over here. So how do we know? And there are a whole bunch of different ways. So the first way that we know is, for instance, looking at the motion of stars. Okay, so let's say we have some galaxy. Okay, and here's all sorts of stars that are sitting. There's all the visible matter, and we look at how things are sort of moving around over here, and we can estimate what's out there by a variety of different ways. One way is, of course, just to look, right? We can see all the visible matter that's there. We have stars and we have dust. But another way is to look at the motion of stars, because the motion of stars is affected by how much gravity they feel, and gravity, of course, cares about how much stuff is out there. So basically, we can look versus considering the motion, and what we find is that there's much more out there exerting gravity on us, making us move in a different way than what would just be explained by the visible matter that we have. Okay, so you've probably seen a figure like this in your life, where you look as a function of, let's say, a radius, and you look at the velocity, and you know that from Kepler's law, things should have sort of been falling off as 1 over r once we've encompassed all of the mass that we see, whereas observationally, things sort of flatten out over here. Okay, so this is what we observe. And what this tells us from these galaxy rotation curves is that something is out there. Something is out there permeating the galaxy and extending to its halo. Extending to its halo. Okay? So this is one way that we know how much dark matter we have. We see it in the motion of stars. We also see it in gravitational lensing. Okay, so we also see it in lensing, where we know that something is out there bending and twisting light, making groups of galaxies look sort of stretched and bended. So for instance, there's a really cute one that you can try to look up online. So if I have let's say some galaxies over here, a group of galaxies, then something is lensing and making these look like, for instance, there's something that makes it look like, let me just try to draw it here. It's called the Cheshire Cat group, so it kind of looks like the Cheshire Cat from Alice in Wonderland. Okay, so something is out there bending and twisting light. Okay. Now we also know that there's dark matter from colliding clusters like the bullet cluster. So from colliding clusters like the bullet cluster, where if we look at these clusters, in particular, for instance, the bullet cluster, then you look, at let's say the gravitational center of the system. So there are there is colliding clusters, these two things like these two pancakes that are coming towards each other. And what we see afterwards is that, let's say the gravitational center of the system is here. Gravitational center is here. But if we look at what we can see, the visible center of the system is offset from it. Okay, so let's say like this. Okay? So again, there's an offset over here, and that's telling us that there's something additional that's exerting gravity. And we also know from very accurate measurements that we have these days from the cosmic microwave background. So we also have the cosmic microwave background, the CMB, and this is, we have very accurate measurements of the power spectrum, which is basically telling us, something like the temperature fluctuations versus angular scales. And you can kind of just think of this, it's telling us how densities around us are correlated at different angles. And so you've probably also seen there's this very pretty plot that has, if I look at some temperature fluctuations as a function of some angular scale, then we have a prediction and we have beautiful measurements, and they're all sort of sitting spot on. Okay, and this power spectrum is very sensitive to the curvature of the universe, so the total amount of energy that we have, also to the particular number of baryons that we have of matter and of dark matter. So combined, the fact that these predictions are coming out, sort of spot on with the measurements. Okay. This is also telling us that we have dark matter and exactly how much we have. And I'll just add over here that if you're interested in learning, I'm sure there are many places where you can read more about this, but there's I'll be trying throughout our lectures to give you references that I think are sort of useful for particular points that we're discussing. So for instance, if you want to learn more about from a particle physics perspectives about these different pieces of evidence, then I highly recommend there's a set of lectures that you can find on YouTube by Roni Harnick. These are lectures that he gave at the Mainz Institute for Theoretical Physics, MIT School. I think it was in 2016. The topic is, of course, dark matter, and I recommend, so it's lesson number 1, has a lot of discussion about evidence for dark matter. So if you're interested, I recommend watching those. Okay. So these are some of the pieces that tell us that we have some of the sort of pieces of evidence that tell us that we have dark matter. So let's now sort of take together and write sort of a laundry list of what are the properties of dark matter that we know. So properties of dark matter that we know. Well, we know, as we said, we know that the universe is dark. Okay, and so I'll write down omega dark matter, which is the fraction of the energy density that's sitting in dark matter compared to the critical density, which is for a flat universe, which is what we have, which is also just the total amount of energy that we have in our universe. This is equal to, measured to be 27%. Okay, and as we said, this is written another way, and again, we might use these things interchangeably. This tells us that rho dark matter is around 5 times the mass density of baryons, and in a local environment, locally, so I can write this as rho dark matter, the measured value is around 0.3 GeV per centimeter cubed. And so basically, if dark matter is, let's say its mass is of order the mass of the proton, what this means is that there's roughly 1 dark matter particle in your cup of coffee. Okay? What else do we know? Well, we know that dark matter has to be massive, but we have no idea, and I really want to stress this, what its mass actually is. Okay? If we think about some scales here of what is its mass, what are the possibilities for its mass? Let's say GeVs. Then up here it's something like between 10 to the 50 and all the way down to 10 to the minus 30 GeV. Okay? When dark matter is if it's above 10 to the 50 and it can microlens, it ruins globular clusters. And if it's at the 10 to the minus 30 bound, which is probably a little more familiar, this is where what we call it's too fluffy. And what it means is that the wavelength exceeds the galaxy sizes, so it can't be, it can't be sitting in the galaxy and we absorb it that way. Okay, so wavelength exceeds galaxy size. Okay, and so if I look at these two endpoints that we've drawn here for the mass, there's around 80 orders of magnitude in which the mass can reside. Okay, so that's really pretty crazy if you think about it. Okay, and in particular, obviously, if you've ever heard a talk about dark matter in your career, then you've probably heard about very particular mass ranges. And we're going to explain why we're going to see how those emerge. But I do want you to keep in mind that there are 80 orders of magnitude in which the dark matter mass can be. Okay, so we by no means know what the dark matter mass is. What are some other things that we know about dark matter? Well, we know that it shouldn't interact too strongly with known forces. with quantum electrodynamics or quantum chromodynamics, because, of course, if it did, we would have already detected it. So it shouldn't interact too strongly with quantum electrodynamics and quantum chromodynamics. And we also know that it shouldn't interact too strongly with itself, because if it interacts very strongly with itself, then this sort of distorts the dynamics in dark matter halos as dark matter sort of bumps into each other. Okay, so it should not too strongly interacting with itself. And as we're going to see, hopefully, on our third lecture, I'll just mention that, of course, this is actually something that could be a potential signal of dark matter, and we're going to see this later. Okay, to what extent some amount of strong interactions might be okay, and maybe that's actually predictions of certain classes of theories. And also, very importantly, is that we would not be here without dark matter. Wouldn't be here without dark matter. Okay, we owe our existence here to ask these questions about what is dark matter. Our very existence here relies on the fact that there is dark matter in the early universe. It plays a very important role in our early universe cosmology in helping structure form and structure grow. So the picture that I want you to have in mind as we're going through this, as we're going through these lectures. So here's the picture. Okay, so basically, we're here in the Milky Way. We're in a disk, okay, and our disk is rotating. So here's my let's do this as a here's my rotating disk. Okay, we're rotating around. You can kind of think of this. I'm in Israel, so kind of think of this as like a rotating pita. Okay, here's my rotating pita that we're sitting on, and around us we are surrounded by a dark matter halo, by this fluffy halo. So let me draw that. Let's say like this. Okay, so here's my poofy halo sitting all around me. Okay, and so kind of think of it as if we're sitting inside a falafel ball. Okay, a falafel ball. Okay, so that's what I want you to keep in mind. That as we're rotating through this big halo, there's of course a relative velocity between us and the dark matter, and so there's a dark matter wind that is constantly hitting us, and its velocity is set by the virial velocity. So there's a dark matter wind that has velocity that's of order 10 to the minus 3 times the speed of light, and I'm going to be working in natural units throughout this course, so that's just going to be indicated by 10 to the minus 3. Okay? So this is what we know about dark matter, and what we're really after, what we want to know, we want to know, what is it? Okay? What is this particle or particles? What are their mass? How do they interact with each other? What sets the abundance of dark matter that we observe in our universe today? So we want to understand what kind of mechanisms in the early universe can set the abundance. Of course, we want to understand, once we have mechanisms, we want to understand what type of model building can we do, what type of theories actually realize these ideas. So there's work to be done for model building. And of course, we also want to understand how can we detect these particles. Okay, and side note, of course, related to this are what are the existing constraints that feed into understanding where we're pointed to in identifying what dark matter is. Okay, so having sort of set up what we know and don't know about dark matter, let's move on to talking about a dark matter cheat sheet. Okay, so here is dark matter cheat sheet. Okay. So first thing that I hope you all know is that we are living in an expanding universe. Our universe is expanding. So, if I have some distance L at a certain time, then it's now being stretched out to some distance, let's say L tilde, that I'll call A times L. So A is what we call the scale factor. Okay? And so if I think of some volume of space, the volume is expanding like a cubed because it's three-dimensional space. So volume expands as a cubed. And if so, what this means is, let's say I have some line element or some metric. I have some ds squared equals dt squared minus a of t squared dx vector squared. And I can define something that's related to this to the scale factor, which is called Hubble. And this is defined to be, so I denote it by capital H, and this is defined to be a dot, so the time derivative of a over a. Okay, so 1 over a dA dt. And this is Hubble. Okay? And as a convention, although it's probably not going to come up much in our course, is that a today at t0 is 1. Okay? Now, if you look at the first Friedmann equation, then if we have no curvature, then Hubble squared goes like the energy density, rho, in the universe over 3m Planck squared. And if you're not familiar with the Friedmann equation, that's totally fine. My goal over here in providing you with this cheat sheet is giving you all of sort of the baseline scalings of things that we're going to need in order to move forward in the course. Okay? And so we know, because we've measured in our universe, that we know that we can write down our energy density as some black body spectrum. So that's just a t to the fourth, where t is the temperature of our photons. And so what we're going to be using throughout is that anytime we have Hubble, it scales like temperature squared over m Planck. And you're going to see very often here I'm going to be using these squigglies. I'm going to be caring less about putting in properly the order 1 factors. I want to show you, give you the tools to understand how things scale and how we can easily and quickly sort of get rough estimates for what type of properties we're going to be pointed to in each of the cases that we discuss. Okay, so that's this is Hubble. So let's box this off. This is going to be so this is our Hubble parameter, which so Hubble is going to go like t squared over m Planck. Now, of course, our early universe is a thermal environment. Early universe is a thermal environment. Okay, and so if we want to talk about some particular species, some type of particles in thermal equilibrium, so for some species that are in thermal equilibrium, we can write down a phase-space distribution. And I'm sure you're all familiar with what this phase space looks like. So the phase space distribution in equilibrium as a function of some momentum p is just 1 over e to the e minus mu. E is the energy, mu is the chemical potential, divided by the temperature. And then there's plus minus 1, where it's plus is for fermions and minus is for bosons. Okay? And from this, once we have a phase space density, we can construct number density and energy density. So we have number density, which is n equals g integral d3p over 2 pi cubed over the phase space distribution. And we also have energy density, which I'll denote by rho, and that's g integral d3p over 2 pi cubed, the energy times f of p, where this g that I've written down over here, okay, this g over here is just the number of internal degrees of freedom. Okay, so that could be, spin, polarization, color, etc. Okay, all the internal degrees of freedom that species carries. So what I want you to keep in mind from all of this discussion is just the following. So again, just sort of trying to give you the ballpark over here, is that for a relativistic species, the number density goes like t cubed, and the energy density goes like t fourth. So this is for a relativistic. Okay, and for the non-relativistic case, you get that the number density is g times mt over 2 pi to the 3/2 e to the minus m minus mu over t. Okay, so this is for non-relativistic. And likewise, rho is m plus 3/2 t times n, and this is just going to be m times n. Again, when it's non-relativistic, what I mean is that the mass is much larger than the temperature. Okay? And so what you see over here in particular if I'm in a situation where I have rapid number changing processes, so the chemical potential of a species is 0, then the number density is exponentially suppressed. Okay, it goes like an exponent of minus m over t. Okay, so it's exponential suppression of the number density. Okay, so if a particle is relativistic, its number density scales like t cubed, there's a lot of it, and if a particle is non-relativistic, once the temperature drops beneath its mass, the number density becomes exponentially suppressed. And that's going to be something that will be useful for us to remember as we move forward. Then a couple more definitions from our for our early universe cheat sheet. We also, of course, care about entropy. So I can define an entropy density. And that's usually defined by little s. So the numbers here, so it goes like 2 pi squared over 45, something called g star s, which is the number of degrees of freedom entering, effective number of degrees of freedom that enter on this entropy, times t cubed. And again, importantly, is that this scales like t cubed when I have relativistic particles in my bath. And this g star s is just, it's the sum over all of the relevant degrees of freedom that are relativistic. So it's a sum over all the bosons in the systems with the relevant number of their internal degrees of freedom, their temperature I over the temperature of the bath cubed, plus 7 over 8, sum over the fermions, again gi, ti over t cubed. And I can define something similar also for the total energy density. So total energy density, also just to give you over here the prefactors, although we're for the most part not going to be using them, it's g star pi squared over 30 t to the 4th, where this g star is like g star s, but replace these ti over t. Instead of to the 3rd power, it goes to the 4th. Okay? You know what? Maybe let me write that out explicitly instead of, oops, just to make sure there are no mistakes. So it's the sum over the bosons of gi ti to the t to the 4th, and then plus 7/8 sum over the fermions, gi ti over t to the 4th. Okay?
Unit?
Yes.
There's a question. Could you state again the difference between the g that we used before and the g star? Okay, you are defining now. So the g that is in the equation of n, for example. Right.
So the g that appears in n is the, so this is the number density of a particular species. And that is the number of degrees of freedom in that, that particle holds. So if it's a real scalar, it's 1 degree of freedom. If it's colored, then it also contains the color factors. Okay, that's for a particular species. What I'm writing down now here, entropy. Entropy is conserved across a sector that's talking with itself. So it's not the entropy of one particle; it's the entropy of the bath of particles that we're talking about. And so there's some effective. So in principle, it's the sum of all the components, and so there's like the effective number of relativistic degrees of freedom that are contributing to this entropy. Okay, and so you see that this GI that's appearing over here, you see these little GIs that are appearing over here. Each one of these is per species the same as this G that appears in N. But over here, I'm summing over all of them over everything that's contributing to the bath.
Okay, very clear.
Okay?
Thank you.
Okay, so we have a bunch of definitions sort of in place, and again, important over here is less the order ones and more the scaling, in particular with temperature, understanding when something is t cubed, t to the 4th, or exponentially suppressed. And now the last piece that I want us to work through in our cheat sheet is the form of the Boltzmann equation. in general. Okay, so here's a Boltzmann equation. Okay, Boltzmann equation. So the Boltzmann equation describes to us how the number density, or it can also be for the phase space, but we're often going to be working with the number density, understands how the number density is changing as the universe evolves. So how it changes as a function of time or as a function of temperature. Okay, so let's first consider a system that has no collisions. Okay, without collisions. So what I mean is, let's just think of these free particles. Okay. So if I look at a system of free particles, then the change in time of the total number of particles is 0, right? Because they're just free particles. Nothing is happening to these particles. Okay. So the d total number of particles, dt, equals 0. Now, of course, so let's write, so n, the total number, is the number density times the volume. Okay. So so this means that d little n times volume, dt, should equal 0. Okay. But let's also write this out explicitly. So this would be the volume times dn dt plus the number density dv dt, right? Just from the chain rule. Okay? And I remind you, so and let's just write this out again in a different way. So let me now divide by the volume. Okay, so I can write this as dn dt plus n over v dv dt equals 0. Okay? Now, I remind you, the reason that dv dt isn't 0 is because our universe is expanding. So volume is changing with time, and in particular, volume is scaling like a cubed. Okay? And so let's look at what happens to 1 over v dv dt. Then that's just going to equal to 3 over a dA dt. Okay? So now let's plug this in to what we have on top, and what we find is that dn dt, we get here now plus 3n times a dot over a equals 0. And if you recognize from earlier, we had said that this a dot over a is exactly Hubble. Okay, so another way to write this equation, and this is the way that we are going to see it appearing for the rest of the course, is that dn dt plus 3hn equals 0. Okay, this is for free particles. Okay, now if our particles are not free,
sorry.
Yes. Mm-hmm.
There's a question. What guarantees theoretically that the early universe was in thermal equilibrium, or that is a good assumption?
So we know that we have interactions that we just, we know the particle content of our standard model in the early universe, and so we know that we have particles that are in interaction, that have rapid interactions with themselves, and so we know that the early universe was in thermal equilibrium. When we add new particles in, we can ask for them, are they in thermal equilibrium with this bath? Are they in thermal equilibrium with themselves? But basically, as long as we're going to see sort of, we're going to work through conditions as we talk about how dark matter behaves in the early universe. We'll understand, I think, a little bit more about how to assess when things are in equilibrium and when not. But the early universe has, abundant. We have light standard model particles certainly throughout. At any given temperature, there's a certain set of our standard model particles that are relativistic. They're very abundant. They interact with each other, and because these interactions are fast, they're sharing energy with each other quickly, and so the chemical potential is equal to 0 for these particles, and they're reaching thermal equilibrium with themselves.
Okay, thank you.
Okay. Okay. So this is what happens for these free particles. Okay, so this is for the free particles, but if they're not free and we have collisions, then this right-hand side is no longer 0. Okay, and then what we write it down, and this is sort of the general form, is that dn dt plus 3hn equals minus some collision term, okay, which is a function of the number densities. Okay, and so this is the type of equation that we are often going to encounter, and for each case that we discuss, this collision term might look a little bit different. but this describes the type of interactions that are happening in the system. Okay. Okay, so having set up now, I hope, some useful machinery for us to be moving forward with, we're going to start talking about dark matter mechanisms. Okay, so close this off, and let's move to talking now about mechanisms for dark matter. So when I say that mechanisms, what I mean are different types of processes in the early universe that can set the relic abundance of dark matter, explain why we have the amount of dark matter that we have today, and explain what type of interactions caused this relic abundance to be remaining. So these are types of processes in the early universe that set the relic abundance of dark matter. And so what we're going to start exploring today and continue tomorrow, and these are by no means the only ones, I'm going to start with what I'll call the 2-to-2 zoo. Okay. So I'm going to draw a whole bunch of different processes here, and you'll see throughout our lectures, so sometimes, as I said, I'll be denoting dark matter with dm. That should be pretty obvious, but also sometimes the particle, I might denote it by chi. So chi throughout will always be the relevant dark matter particle. And also in all diagrams that I'm going to draw, time is always going to flow from left to right. Okay? So I'm not going to be writing the time arrow throughout. So this is, we're going to start with this 2-to-2 zoo, and I just want to point out that this is only our starting point. By no means, and then we're going to go beyond afterwards. Okay? So let's start drawing some of the types of 2-to-2 diagrams that the people have so far proposed that could be setting the relic abundance of dark matter, different mechanisms for setting the relic abundance. So the first one I'm going to draw is probably the one that's most familiar, and it's people usually call it the WIMP. I'll be more cautious and call it sort of the standard annihilation diagram, but let's draw it like this. So I have two dark matter particles that come in and annihilate in some way, and two other particles come out. I'll call them phi. These phi's are going to be either standard model particles or particles that are in thermal equilibrium with standard model particles, or maybe even their own bath, just two other particles. Okay, so this is what's often called the WIMP. More generally, it's sort of the standard 2-to-2 annihilation. And we're going to be delving and understanding this one in depth for the rest of today. The second case that we could have is, for instance, I take the exact same diagram. Okay, so it's still a 2-to-2, right? I remind you that my time is going this way. So here's my chi, still annihilating to phi. But now we're in a situation where the mass of chi is smaller than the mass of phi. And if this is the case, this is what's called a forbidden channel. And we're going to be looking at this one too. Another option is that, again, we still have two chi's coming in and annihilating, but now instead of annihilating, instead of annihilating to two other particles, they what we call semi-annihilate. So they annihilate to one dark matter particle and one other particle. Okay, so this is what's called semi-annihilations. That's another possibility for a 2-to-2 process that's depleting the dark matter in the early universe. We can also have, so again, I still always draw this 2-to-2. So instead of having just one chi, one type of chi, one type of dark matter particle, maybe there's a whole tower of them. Maybe I have some chi I and chi j that are annihilating together, and they're going to phi. And this is something that's called co-annihilations. And we're going to be solving this one also. We can also have something that's called co-scattering, and that's the following diagram, where chi is scattering off of some other particle, phi, and changing its identity to be some other particle, psi. This is called co-scattering. And I'll also add over here, there's another process which could be the following. So again, 2 to 2. I could have chi annihilating with some other particle phi and going to 2 phi's. So you see here that the phi kind of ate up the chi and turned it into another phi. And this is from a recent work that are called, these are called zombie annihilations, okay, because the phi is the zombie. It's meeting a dark matter particle and turning it into another zombie. And there's one more 2 to 2 that I'll write down over here. Again, a 2 to 2. This is, I could have chi that's elastically scattering off of phi particles, and this is called the elastically decoupling relic, or in short, it's called an elder. It requires, I'm going to kind of put this in parentheses, it requires another process happening in the background, as some of these others do as well. So that's the elastically decoupling relic. So these are kind of giving you the picture of the 2 to 2 different 2 to 2 mechanisms that have been proposed and worked out so far in the literature. And what I want to do is we're going to walk through a few of these to understand. The ones that I've chosen for us to walk through together are each meant to give you to sort of enable you to develop some tricks or some methods to understand to really understand how you can quickly figure out what works and what doesn't work, and if it works, what type of mass scale and interactions it points you to. And also certainly to sort of open your minds so that you will hopefully in the future be writing down other 2 to 2 or other interactions that could be setting the relic abundance that people just haven't thought of yet. Okay. So with this in mind, we're going to start with our first mechanism that we're going to do in detail, and that is the WIMP. And I think it's no secret that that the WIMP has been the star of the show for, I think it's already more than 40 years, so for 40 plus years. Okay, and so if you attended a school, if you were listening to dark matter lectures, certainly a decade ago, and maybe even 5 years ago, it might be that most of 4 lectures would be focused on the WIMP and on all sorts of aspects. I think we now understand that the WIMP is just, it's an important type of process, and it's clear why, if you were going to love one process, this would be one that would make sense to be very captivated with. But I want to show you that we're going to walk through and sort of gain a lot of intuition by working through the WIMP case, and then we're going to use a lot of the intuition that we develop to understand these other mechanisms, which, as I said, are just as interesting. They just point to different types of interactions and processes. Okay, so the WIMP, let's just redraw it over here. So the WIMP is some annihilation where chi goes to phi. And here's our diagram. Chi goes to phi with time going this way. Okay. And let's write down, so also, first I want to point out that if this process is very fast in the early universe, then what it does is it sets the chemical potential of one side to equal the chemical potential of the other, right? So if this process is fast, then it sets the chemical potential of chi to equal the chemical potential of phi. And we can write down our Boltzmann equation for this system. So dn chi dt plus 3 n chi h equals, as we said, minus the collision term as a function of this of the number density. So let's write out this collision term. Okay. Actually, maybe just before that, just to mention that, okay, so let me just write this here as a side note, and maybe I'll put it in parentheses, is that if I have a diagram like this, then I can also flip the diagram on its side, and then I have the scattering diagram, right? So then this particle will also elastically scatter. Okay, so I can also have chi phi goes to chi phi, something that looks like this. Phi's over here and chi's are scattering off of them. where we're assuming, you know, that this phi is either some, it's some bath particle. Okay, so it could be that it's the standard model particle, or it could be that it's something that's thermalized with the standard model, etc. Okay, but because it's a bath particle, that's setting the chemical potential to 0, and it has a temperature. Okay, so that's why we can talk about a temperature over here. Thus, has a temperature, and this in turn is going to set, you know, for the whole system, it's going to set that also the chemical potential of our dark matter is 0, and that's going to simplify things for us. Okay, so this is just a side note. Okay, and let's go back to writing down our collision term. Okay. Okay. Maybe actually one more thing about this side note is just to notice that this is something that's going to be sort of a recurring theme. You see, we have this annihilation diagram, and we also have the scattering process. And what you'll find actually is that the kinetic decoupling, the elastic scattering, will always be shutting off after the annihilations. And that's because of the number density that the rate is proportional to. So we're going to be seeing this in detail. Don't forget if you don't understand what I mean right now, but just sort of to keep that in mind, that something that we're going to be seeing later is actually already happening here for the case of the WIM. Okay. But again, if you didn't understand what I said, that's totally fine. Hopefully that'll become a little clearer probably tomorrow. Okay, so let's look at our collision term over here, this C. Okay, so here's my Cn. Okay, let me just write it out once in its full form, and then we're going to see how we're never going to be looking back at that full form. I'm going to be showing you sort of tricks of the trade for this. Okay, so the collision term has the following form. So there's an integral over the phase space of the first dark matter incoming, integral over the phase space of the second dark matter particle, and also integrating over the first final state and over the the second final state. There's some 2 pi to the 4th delta 4 of, you know, sum of incoming momenta minus sum of outgoing momenta. And then I'm moving down here times a matrix element squared that is summed and averaged over initial and final degree of freedom. Let me just write that out. So this is, this is averaged over all initial and final state degrees of freedom. And it's also proportional to the phase space density of the first chi1 that's coming in, of the second chi2 that's coming in, minus the back reaction process, which cares about the phase space density of the first phi1 and phi2. Okay, so this is the general form for the collision term for this 2-to-2 process. And let's just spell out what are these phase space integrals. So this phase space factor, let's say d pi a for some particle, has the number of degrees of freedom that species carries, and it's d3 pa over 2 pi cubed to energy of that particle A. And this is just the Lorentz invariant phase space. Okay, so we wrote out something that might look a little bit ugly, but let's just make sure we understand how all these pieces are coming in and that it makes sense. So let's just see how it makes sense. The reason that it makes sense is because, you know, I have to have, so matrix element squared, that's clear because, you know, I have to have the, in order for the interaction to happen, obviously I have my, you know, my particle physics piece that's coming in. What is the size of my matrix element squared? So that makes sense. So matrix element squared makes sense. These two phase space factors, you know, over here and over here also make sense because in order for this interaction to happen, both of the particles have to meet each other. Okay, so also these, you know, the fact that it's F times F in each case makes sense to us. The fact that we have both of these terms minus each other also makes sense because we have to take into account both that forward process that's producing these particles and also the back reaction process that's taking away these particles. So both of these things are happening in the early universe. And even this minus sign that you see sits up here, this minus sign over here, that also makes sense because if I'm looking at the direction of annihilating, I'm removing particles. Okay, so every single piece in this somewhat complicated expression can actually be understood. It just really makes sense. Okay. Okay, and so roughly what we see, what you see is actually sitting here. I can kind of think of this. This is the language that we'll often use. What we have over here is this entire collision term looks like some thermally averaged cross-section times number densities. Okay? And so let me take all of this, this collision term and write it in the following way. Okay, so let me take our equation that we had before, and I'll write it like this. So I had dn dt, okay, dn chi dt plus 3 n chi h. So I'm going to write this entire collision term in the following form. There's some minus a thermally average cross-section. It's called sigma v with these brackets on the side that are indicating that it's thermal averaging. Okay, and this is for this process chi goes to phi, the annihilation process that we're interested in. And so, and we have here n chi squared, because 2 chi particles have to meet each other in order for this process to happen. And now the question is, what's the next term that's taking into account the back reaction of looking at this process? What happens if time is reversed over here? In other words, also the phi's annihilate into chi. And so over here we use an interesting trick, which is also something that's going to be very useful for us later in the course. So let's use a trick, which is called detailed balance. Okay? And what this means is that when we're in equilibrium, the forward process and the backward process are both happening rapidly. And so we know that in thermal equilibrium, the number density shouldn't change, okay? With the exception of the expansion. In other words, the total number of particles is not changing. So in thermal equilibrium, this right-hand side of our Boltzmann equation needs to vanish. So that's this trick that in equilibrium, the forward and backward processes are both rapid and should cancel out. Okay? And so we can write the back reaction in the following way. I can just write this down. Because I know it has to vanish when chi is in equilibrium, is that n chi, this is n chi equilibrium squared. Okay, so this is how we figure out how to write the back reaction. And that's a trick that we're going to be using later in the course as well. Okay, so we have a Boltzmann equation. Okay, let's just write this out. Yeah, Luca, is there a question?
Yeah. Would the inverse process involve the distribution for antiparticles to have the same amplitude by the CPT theorem?
Well, so right now, in what I'm doing right now, I'm assuming that there's no asymmetry between, I mean, I haven't told you even if this is a particle that has an antiparticle or not, but I'm assuming that if there's an anti-chi, that there's no asymmetry between them. So right now, I'm just writing everything sort of schematically. Of course, once you write down a particular model, you can really track between chi's and chi bars if you have them. But right now, I'm just assuming that I have 2 chi's going to 2 phi's.
Okay.
Okay. So, so for this WIMP annihilation, for this 2-to-2 annihilation process of chi to phi, this is our Boltzmann equation. And now let's sort of understand what happens. Okay, so what is this equation first telling us in terms of what picture is it telling us about what's happening in the early universe? And then we're going to sort of solve it, and we'll see some tricks how to do that quickly. So what is this equation telling us? So what is actually happening? Okay, so what happens? Now to understand this, we're going to do the following. Instead of thinking about particle density in some box, let's think of particle density in a box that's expanding with the universe. Okay, so instead of density of particles in a box, we're going to think of density of particles in a box that's expanding with the universe. Okay, so this is sometimes called the yield. I'm not really going to be using this much, but just for this this particular. So yield is just number density, divided by the entropy, which scales like temperature cubed, which scales like 1/a cubed. So this is just what is number density times a cubed. Okay, so this is sort of the. So I want to sort of scale out from everything I'm describing right now the fact that the universe is expanding. And so let's look at what we have. And again, this is a picture that you've probably seen before, but I want to make sure that we all understand it because it is actually going to be very similar for all of the mechanisms that we discuss. Okay, so let me look over here at number density over entropy. So that's my co-moving number density, and I'll just average it already, normalize it to the measured value. Okay, and instead of looking at a function of temperature or time, people often convert, and it's very useful to look at a variable I'll call x, which is a dimensionless quantity, which is the mass of dark matter over temperature. Okay, and so early times and late high temperatures, early times are sitting over here. Okay, early times or high temperature are sitting at this end, and this is late times sitting over here. Okay. And let's just take a look and understand what's actually happening in the system. Okay, so in the very early universe, very high temperatures, both of these processes of the forward process and the back reaction process, they're happening rapidly. These two sectors are equating. We're just in thermal equilibrium, and basically nothing is changing with our number density. So we're just kind of sitting flat like this. Okay, now at some point, the temperature of the universe drops beneath the mass of the dark matter particle. So in X language, that's when X drops beneath 1. X goes below 1. And at this point, if we look back at, I have these, so here's my forward production process. Okay, chi goes to phi versus the inverse, where 2 phi's go to 2 dark matter. Okay, so in the very early times, both of these processes are happening rapidly, and that's why we have this sort of constant n over s. But once the temperature drops beneath the mass of dark matter, then you see that this production process, okay, versus the annihilation case, the production process, it's very difficult for it to happen, right? Because there's not enough energy to easily produce these dark matter particles because the temperature is lower than their mass, okay? And so effectively, the production process gets suppressed or kind of shuts off, and then dark matter is just rapidly annihilating away, okay? So here we are, dark matter rapidly annihilating away. And, in principle, if nothing else happened, then it would have completely vanished. So this is what happens when we go to the non-relativistic region over here, okay? The production is suppressed. But now I remind you that as the universe is expanding, in order for this process to happen, particles have to meet each other, right? And so at some point, the universe has expanded so much, the dark matter particles are so dilute that they no longer find each other to annihilate, and that's when we're left with a constant relic abundance. Okay, so this is the third piece is over here when at that point we are frozen out, the number density is not changing, the co-moving number density is not changing anymore. This is when particles are so dilute that the annihilations shut off. Okay. So this is, and over here, of course, and this is, if we did our work properly, this is how we're left with some constant relic abundance. And of course, how much we're left to depends on the size of that interaction, the size of our thermally average cross-section, right? If I have a larger cross-section, I'm going to be able to maintain this process for longer, and I'll be left with a smaller amount of dark matter. If the cross-section is smaller, I'll decouple, I'll freeze out earlier. And so how much we have left, so how much is left depends on, is a function of the size of this thermally average cross-section. But for just the right size of this cross-section, we're left with just the right amount of dark matter. Okay? And so this, what we've drawn over here together is sort of what's called the standard picture for freeze out. For dark matter, freeze out. Okay? And this is certainly what happens for these 2 to 2 annihilations. But moving forward, I actually want you to remember this picture because something very similar is really going to be relevant for all of these mechanisms that we're going to be describing together.
Yoni, before you go on, there is another question. Maybe you're gonna explain this later, but in case, can you just elaborate for how to calculate the sigma v in case I have my Lagrangian and my Feynman rules?
Okay, so what we're going to be doing in okay, so at this point of the course, and probably with the exception of perhaps when we talk about some models in our third lecture, I'm not going to be computing to you, given a theory, compute the cross-section, matrix element, and integrate. What I want to show you is how to understand. So the next step that we're going to do is understand what is the size of the cross-section that we need in order to match onto the observed relic abundance. And then for any given model that you write down that falls into this, where this is the process that's controlling the relic abundance, you can work out what is the cross-section by computing your Feynman diagrams. You can work out what is the cross-section in terms of the parameters of that model. But what we're doing right now is talking about the mechanism level, not talking about particular models that fall into this category. So for instance, supersymmetry is perhaps the most well-studied example of a theory that gives 2 to 2 that has dark matter that falls into this category. It has dark matter that's described by that the process in the early universe that's at the abundance is a 2 to 2 annihilation. But there are literally like millions, or there's like an infinite number of models that one could write down. We're not going to be writing down models right now. What we're doing is describing the mechanisms, understanding what size of a cross section does the mechanism point to. What type of mass and interactions does it tell us? And that will feed then into what type of signatures we could have, what type of constraints it has. And also then once you go ahead and write down a particular model realization of this mechanism, then you can figure out what are, in terms of the couplings in your particular theory, how does that map onto the general case that we're doing over here.
Okay, thank you.
Okay, so now that we have a picture of what is freeze out, what's happening, how the system is evolving, let's try to understand what size of a cross section we need in order to get this to work, in order to explain the relic abundance that we've observed in our universe. So for that, we're going to be performing a back of the envelope estimate. Okay, and this is a type of trick that we're going to be using very often, and is super useful whenever you think of some new process that could be realizing your explaining the dark matter abundance, and it's the following trick. Okay, so I ask myself, if I'm a dark matter particle, okay, and I want to know when am I freezing out? Okay, so that's focusing on this this. If I go back over here, it's on this region over here of exactly when am I departing from my equilibrium number density and starting to go and just freezing out, okay? And so freeze out roughly happens, okay, so freeze out, which I'll often denote just by F0, freeze out happens when the rate for this 2 to 2 annihilation is of order Hubble, is of order the expansion of the universe. And that's kind of like saying, what it means is, in order for me to be frozen out, that means that basically by the time the universe is expanded, I haven't yet met a particle. Okay, and the way to think of this is really as if I'm a dark matter particle, and now I can ask myself, what needs to happen in order for a collision to happen or not happen. Okay, so let's write out what this 2 to 2 rate is. So the 2 to 2 rate goes like the number density of dark matter times that thermally average cross section. Okay, so again, if I'm a dark matter particle, then in order for this 2 to 2 annihilation to happen, I have to meet another dark matter particle. That's why there's 1 power of n chi, and I have times the interaction strength. So that's my thermally average cross section. And I'm freezing out when this rate is of order Hubble. And I remind you, we said Hubble scales like temperature squared over m Planck. Okay. So as we said, the fact that we have just 1 power here of n chi is because think of yourself, think of what a dark matter particle needs to happen. Okay? And so what I want us to do now is, what I want to note is that a trick that we can do, okay, one way is, of course, to solve the whole, to solve the Boltzmann equation properly, and that's something that one should always do when you're actually figuring stuff out in depth. But what I want to give you is, I want to show you some tricks for how you sort of get a sense of what's going to happen, and these actually also correspond pretty well to when you exactly solve the Boltzmann equations. Okay, and so the trick that we're going to do over now is to relate. We're going to relate this, the number density at the time of freeze out, to measured quantities. Okay, and the other sort of piece of this trick that we're going to do is to consider, we're going to start playing with redshifts. Okay, so we're going to redshift from different times, from different temperatures, to sort of to reach things that we know and we can put together. Okay, so so in the system, the entropy. Okay, so the entropy, the total entropy of the system is conserved. Okay, and so what that means in total entropy is, entropy density times scale factor cubed, and so this has to be a constant. And so what we do is we use either entropy or A cubed or temperature cubed to redshift between different times, between different temperatures. Okay, so we use this to redshift. So let me, S, that means that S goes like 1 over A cubed, or alternatively like T cubed, and you can also see from here that this is telling me that my temperature is going like 1 over scale factor. Okay, so let's look what happens here. So after freeze out, if we look what happens here after freeze out, my co-moving number density, that's N over S, that's staying constant, right? Okay, so we can redshift it from today, where we've measured it, all the way back to the time of freeze out. So let's do that. Okay, so the co-moving number density, okay, that's the same thing as the yield of dark matter is constant. Okay, so we're going to redshift from today to the time of freeze out. Okay, so here's my n chi at, so it's today, so at t naught or x naught, that's today. So I can write this as n chi at freeze out. So freeze out I'm going to denote with a capital F. Okay, so xf is x at the time of freeze out, which is mass over t freeze out. And then I'm just redshifting by inserting here the ratios of entropy density today versus entropy density at the time of freeze out. Okay? And so if I just plug in, let me denote this equation that we had over here before, this equation with our rate, where 2 to 2 rate equals Hubble. So what we had over here, remind you, was this was all at freeze out. So the number density that appeared in this equation is n at freeze out. So let's just substitute what we get from this star equation into where we're writing right now. And so what this just equals is Hubble at freeze out over sigma v times, this part I don't touch, s of x naught and s of x freeze out. Okay, all I did was insert dark matter density at freeze out from the star equation into the equation that we're writing right now. Okay, now today dark matter is non-relativistic. Dark matter is non-relativistic today, so we can write the energy density in the following form. So omega dark matter, which right now we're calling dark matter chi. So this is the energy density that's sitting in dark matter over the critical density. So I can write the energy density just as mass times number density because it's a non-relativistic particle. And then, and this is all happening today, right? So this is today. I mean, this whole equation. Sorry, it's not just this particular. Right? This is something that we measure today. So this is today, okay? And so let's plug in what is number density today. So let's maybe indicate this equation here with, here's my two-star equation. Okay, so let's plug that in here. number density today equals, so I'm going to have here m chi over rho Kriti. That's not changing. And now I have what we wrote in this two-start equation, which is Hubble at freeze out over sigma v, S today versus S at freeze out. Okay? And now all we have to do is plug in, we know the scaling of let's just write this in. So, so we know that, so Hubble, right, Hubble we said was t squared m Planck. So I can also write this, if I want to move to this x variable, which is m over t, then I can write this as m chi squared over x freeze out squared m Planck. I remind you that entropy density had a scaling, let's be more careful. The entropy density at freeze out scales with temperature cubed. So entropy density at freeze out scaled with temperature cubed. So again, I can write this as mx cubed over x freeze out cubed. And we just plug in the values of the entropy density today that we've measured in rho Kriti. I'll just write those out for you here in case you want to try to reproduce it yourself. So S naught is something like 2.2 times 10 to the minus 38 GeV cubed. And rho Kriti is around 1.053 times 10 to the 5 h squared GeV over c squared centimeter to the minus 3. And h is ballpark of 0.7. Okay, so you take all of this type of stuff and you plug it in. Okay, let's see what we get. So what we get is that when we just plug this all in, is that rho dark matter is the following. So it's x freeze out over 20, 10.75 over g star to the power half. And then I have here 10 to the minus 9 GeV to the minus 2 over sigma v. Okay? Now, the fact that I've pulled out these scalings for x freeze out and g star is just because I'm putting down some numbers. And so the next thing that we're going to do together is try to understand what values of x freeze out we're pointed to. Okay? And you'll see the answer is ballpark of 20. That's why I've scaled it this way. And then we're going to be able to understand what size cross-section is needed. Okay? So let's look at what value do we expect to get for x freeze out, which is the same thing as saying what temperature versus mass does, at what temperature does freeze out occur, okay? How much below or above the mass of the particle are we freezing out? So the way that we can do this, and this is again really going to be similar for all of the different mechanisms that we talk about, let's assume that it's really instantaneous freeze out, okay? So if I scroll back over here to our plot, the region where this curve is starting to depart from the equilibrium density, obviously it doesn't happen like in an instant, but let's imagine for a second that this happens in an instant just so we can get sort of a feel for what's going on. So let's assume that's called instantaneous freeze out approximation. Okay, so what value is xf? So let's assume instantaneous freeze out. And so what we do is we can plug in into our rate equation, plug in the equilibrium density for for our chi's at freeze out. Okay, so that's sort of a good approximation that I'm in equilibrium and then I freeze out. And so let's look what this tells us. So we had this this equation beforehand. We had n chi. Let me assume that it's in equilibrium at the time that it's about to freeze out. At the time of freeze out times sigma v, and this had to equal Hubble at the time of freeze out. Right? This is just that equation. Scrolling up here, it's the start equation that we've written up here. Okay. So let's see what's happening. Okay. So let me assume that the particle is non-relativistic, and that's indeed in this plot that we've shown it should be relativistic, non-relativistic, and we'll also make sure that this makes sense when we get our final answer, that it's consistent. So my number density had number of degrees of freedom in this particle, and I can write it as m chi squared over xf 2 pi to the 3/2 e to the minus xf. Okay, this is just the non-relativistic number density that we saw earlier on, written instead of in terms of m over t. I've now written everything in terms of x's. I've replaced temperature with m over t, and times sigma v, and this should equal T freeze out squared over M Planck, which I can also write, as we said, as M chi squared over X freeze out squared M Planck. Okay? And so the only thing that's really important here is because it's non-relativistic, you see that I have this XF that's sitting up here in my exponent. Okay? And so when I solve for XF, what we're going to find is that XF goes like a logarithm of all of these parameters. Okay, and I'm not even going to bother writing out all of the factors of all the parameters, because the fact that it's only logarithmically sensitive to them is telling us that for a broad range of these parameters, we're always going to get roughly the same number. Okay, so the freeze out temperature, or XF, which is mass over temperature, is roughly the same. It doesn't change much over a broad range of parameters. Okay? And so in particular, for pretty much all of the cases, definitely for this case and for all of the cases that we're going to be seeing, X freeze out is typically a factor of 20 or 30 for dark matter masses that are, let's say, between the MeV and TeV, or even higher masses. Okay? So what this means is that dark matter is always freezing out non-relativistically at temperatures that are roughly a factor of 20 beneath its mass. Okay, so dark matter is freezing out. That's what we just arrived at. That dark matter is freezing out when it's non-relativistically temperatures that are roughly a factor of 20 beneath its mass. Okay? Okay, so having concluded that X freeze out is indeed of order 20, then I go back and look at our the relic abundance that we wrote down for omega dark matter, and now let's remind ourselves that we wanted the correct relic abundance was that omega chi was 27%. Okay, and so what this tells us, if we plug back in, is that the size of this thermally average cross-section is of order 10 to the minus 8 GeV to the minus 2. Okay, so this is the result that we get for this 2-to-2 annihilation process. And the reason that this number is interesting and has been the star of the show for so many years is because this is roughly what you would expect to get if this cross-section was of order an electroweak cross-section, or if dark matter was interacting in a strength that's similar to the weak force. Okay, so this is roughly what you'd expect to get for a weak force interaction. Okay, and so this is what's called the WIMP miracle. Weakly interacting massive particle, or in short, the WIMP miracle. And this has been the dominant notion for dark matter for over 4 decades. Luca, is there a question?
Yeah, please. The student is asking whether these results that you're getting, numerical results, do depend on the initial abundance conditions or not, because it seems that everything is depending on the washout temperature. Well, so what's beautiful, so the WIMP is one example of what we call a thermal relic. Okay, so it's a particle that in the early universe was in thermal contact with the standard model. And what's beautiful, and the reason that thermal relics are so appealing, is that there's no dependence on initial condition. In other words, if I'm in equilibrium, then I'm always, then my initial condition is basically set to be a thermal distribution. Okay, so there's actually no dependence here on the initial condition. It's a thermal relic. It's in thermal equilibrium in the early universe. And once I have these types, once I want to talk about a particle that has this, if I have this type of interaction, then thermalization is just what naturally happens.
And this is, of course, only one example of a thermal relic. We're going to be seeing several more.
Okay, thank you.
Okay. Are there any other questions?
No, for the moment, that is the only one.
Okay, great. So, so let's see how much of this next. Okay, I think we should be able to do the last bit for the WIMP. Okay, so we've arrived now at what the size of the cross section is if this 2-to-2 process is in charge of the relic abundance, and we understand now why it's called, hopefully, why it's called the weakly interacting massive particle, or the WIMP miracle. But what I'd like to do now is show you a different way, an alternative back of the envelope method that's going to be also very useful for other things that we do, and I think it also sort of emphasizes why, in a way, this is a miracle. Okay. So let's write out here an alternative. Let's write an alternative back of the envelope. Okay. And the trick is that we're going to redshift through T equality. Okay, this is of order 0.8 eV. T equality is the point of matter radiation equality. Okay, matter radiation equality. Okay, so this is the point when the energy density sitting in matter, total matter, baryonic and dark matter, equaled that of radiation. Okay. So this is the alternative trick that we're going to use. So, and let me also parameterize. Let's parameterize our thermally average cross section sigma v. So this is a 2-to-2 annihilation process, right? So let me just parameterize it. I parameterize my ignorance because I haven't written out a model with a Lagrangian, a detailed model that's giving it to me. Let me just describe this effectively as some effective alpha squared over m chi squared. Okay, it's a 2-to-2 cross section, so dimension wise it's 1 over mass squared, and I'm just putting in some effective coupling constant that's describing, effectively what this thermally average object that sits in my Boltzmann equation is. Okay, and so let's look what happens at matter radiation equality. So at matter radiation equality, so at matter radiation equality, we said is that rho, the energy density sitting in matter, equals, so this is equality right now, not equilibrium, it's at equality. So let's make sure equality. So this equals the energy density that's sitting in dark matter plus the energy density that's sitting in baryons. Okay, and because it's at equality, this is, by definition, it equals the energy density sitting in radiation, in other words, sitting in photons. Okay. Now, I remind you that we know, so dark matter, we know the dark matter density today, and we know that, right? So rho chi is, as we said, ballpark of 5 times the mass density that's sitting in baryons, and we also know that it hasn't changed. If it froze up before T equality, it's unchanged. And so what this means is that, again, I'm sort of throwing away order 1s here because that's not the point, but you can even see from how we're doing it how you would track these order 1s. So let me just equate that rho dark matter at equality is the ballpark of rho photon at equality. Okay, where you see I've dropped this order 1, where in principle I could be tracking these order 1s as well. Okay, so we've neglected the order 1s over here, and now let's use this for the following things. So I want the number density, right, for our freeze out condition. We want the number density of dark matter at freeze out, and what I can do is redshift from freeze out to T equality, to matter radiation equality. So this will go like the number density at T equality times either I redshift with entropy or equivalently with temperature cubed. So let's do temperature cubed here. So redshifts with T freeze out over T equality cubed. And so I can write this as, right, so the number density of dark matter, it's non-relativistic, so I can write it as rho over m. So the number density is rho dark matter at T equality over m chi. And the next piece doesn't change. I have here T freeze out cubed over T equality cubed, cubed. Okay, and now I remind you that, So now let me use this fact that we wrote over here. that at equality, up to order 1s, energy density in photons is the same as energy density in dark matter. Okay? And so let's write that in the following way. So let me now replace rho chi with rho photons at equality. Okay, and the rest stays the same over m chi, T freeze out cubed over T equality cubed. And now let's use the fact that we know the photons are just a black body, so they scale like temperature to the 4th. And we plug this in, and what we have now is T freeze out cubed T equality over m chi, because we canceled out factors of T equality. Okay? And let's write this again another way. Instead of T freeze out, let me write it as m chi squared over xf cubed times T equality. Okay, so this is how we've redshifted our number density of dark matter at freeze out and written it in terms of T equality. And we could do this because we use the fact that we've measured. So we're using a measured quantity, which is a relic abundance of dark matter, up to the fact that I've dropped order 1s here. Okay? So this is the number density at freeze out. And now let's plug in this number density into our freeze out condition, rate equals Hubble. So let's plug into our freeze out condition. So that was this equation that had 1 star from earlier before. And so the rate, I remind you, the rate for this 2 to 2 was the number density at freeze out times the thermally average cross section, which I parameterized here as alpha effective squared over m chi squared. And now I plug in this new expression that we found for n chi at freeze out, which was m chi squared, excuse me, over x freeze out cubed times T equality. Okay? And now I have to do times alpha effective squared over m chi squared. So you see that m chi squared is canceled. Okay, and now I have to insist that this is equal to Hubble at freeze out. And Hubble at freeze out is just T freeze out squared over m Planck. And I can again write this in terms of x as m chi squared over x freeze out squared times m Planck. And so now I equate my left-hand side and my right-hand side, and we solve for m, and what we find is that m chi goes like alpha effective times square root of T equality and m Planck. Okay? And in particular, if you take care of the order 1s, so just to give this numbers, this goes like alpha effective times around 30 TeV. Okay. And so you see here that it happens to be the case that if this coupling that we've written down that's controlling the 2 to 2 annihilations is of order an electroweak coupling of order 10 to the minus 2, then the scale that emerges for dark matter is around 300 GeV. Okay, so the scale that emerges for dark matter is the weak scale. Okay, so this is if alpha effective is of order 10 to the minus 2 of order a weak, of order the weak interaction, then the weak scale emerges. Okay, and this is the WIMP miracle. Okay, and what I really want to stress, that I hope is clear here, that this is a coincidence of scales. Okay. I have two unrelated scales, T equality and m Planck, that contrive together to give me a geometric mean, which if I plug in a weak-sized coupling, give me the weak scale. Okay? So I just want to stress this. This is a coincidence of scales. Of m Planck, two unrelated scales, m Planck and T equality. And I also want to point out that although this regime where the coupling is of order a weak coupling, which gives us the weak scale, this is by no means the only thing that I can do here, because if I take a coupling that is larger or smaller, I get masses that are larger or smaller. Okay? So in particular, of course, also that if I take, for instance, this alpha effective to be much smaller than a weak interaction, I naturally get dark matter that is, of course, also much lighter than the weak scale. Okay? So Luca, is it okay if I take another few minutes to finish this point?
Of course, you can.
Okay, great. Okay, so I just want to point out that another way that I can write the result that we just arrived at, another way that I could write this is the following. Okay, so we see this relationship between mass and coupling. If I just think of how we've defined this thermally average cross-section, which was this coupling squared over m squared, this just has to scale like 1 over t equality m Planck. Okay, so that's sort of another way to be writing this result. Okay, the size of the cross-section that's needed is 1 over t equality m Planck. Okay, and the last thing that that's relevant in this context is that there's, in principle, an upper bound that you could think to set on dark matter, on the dark matter mass through this annihilation process, and that's often referred to as the unitarity bound. Which is the statement that, at least in terms of this effective coupling, and this is why it's not always really 100% true, but couplings are typically not larger than 4 pi, right? That's sort of where unitarity breaks down. And so this could give you an upper bound on the mass of the dark matter that's of order 300 TeV. Okay, so this is what's called the unitarity bound, and it dates back to a very famous paper by Greist and Kamiakowski in 1989. And I just want to point out that only really recently, in the last maybe year or two, people have realized that there are ways to evade this bound, even for a thermal relic. And so I'll just point out, in case you're interested in reading about that, a couple of references. So there are ways to evade. In other words, to have thermal relics that are with a mass that exceeds this by, I think the current ones go up to 12 orders of magnitude. Okay, so that's definitely a very big deal. So I'll just mention, I'll give you guys 2 references over here. So one is called Super Heavy Thermal Dark Matter, and it's a paper by Kuflik and Kim in a PRL from 1906.00981, I believe is the reference. So that's the first one. And the second one is a process that we've actually written out already, the zombie process, which is written by Kramer, Kuflik et al. And that was also a PRL just published very recently. I think it's 2003 04900. Okay, and so what you see generically from this process that we've studied, which is often called the WIMP, but it's by no means actually the weak scale or the weak interaction itself, is that we understand what size the cross-section has to be. There's a particular relationship between the mass and the coupling in this process, and this can give you dark matter masses that are of a whole broad range, even beyond what's considered the unitarity limit. Certainly, typically, and we'll be talking about this towards the end of the week, we have reasons for thermal relics to sort of be considered to be above a keV or an MEV, but you can sort of think of this, that they can go above, and often it's thought of that they can only go up to masses of around 300 TeV, but as I just said, there are certainly caveats to this statement. So that's all I wanted to discuss with you guys today about the WIMPs, and thanks for your time.
Thanks to you, Yoni. I don't know if there are questions. Yeah, there is. There is a clapping. Sorry, this is automatic. This is Siri. Are there any questions? So in case you have late questions, we can start with those ones tomorrow. I think we can stop here today. And thanks again, Yonit, and see you everybody tomorrow morning at 10.
Thanks, everyone. Take care.
Thank you. Bye.